Alright, so let's talk about how generalize the knowledge about distribution of mean values to the difference of means. So I'll just recall you that in the previous video we discussed how to estimate uncertainty of outcome for every population. So we have sample from this population, we have sample from this population, right? And this is the confidence intervals for the average amount of, for the average percent of popped corns. Our task is to estimate the possible effect, so the possible difference of these outcomes. So how to do that? So first of all, let me show you some intuition. You remember that this is what we are looking for. It's a theoretical effect. This is the observed effect. This is what we can compute. And then this is our assumption. It's not necessary, strictly speaking, for all these calculations, but I'll keep it. So we assume that the standard deviation of population is the same. Because we didn't change any external factors, we changed only this one of the systematic factor. We actually don't change, we shouldn't change any random variation in this case, right? Now let's recall again that the average of the first sample came from normally distributed population. So this is just a short way to write that this value is from normally distributed population. And these are parameters, right? So this is mean, this is average. And this is variance. So instead of standard deviation, I use variance in order to get rid of the square root, right? So this is variance. You remember that variance for mean, we call it standard error squared, and it's simply the variance of your population divided to your sample size. You remember that standard error is sigma divided to square root of n, and in this case, if you square it, you will get exactly this variance. Okay, so this is the theoretical expectations, but we know that because we don't know sigma, we can approximate it using t-distribution. That's how we do it, right? So instead of normal distribution, we use t-distribution. So in this case, we have a sample average, population average, t-value which follows t-distribution. This is a randomness, right? And the standard error estimated based on the sample statistics. Likewise, we know it about the second population. So the second population, again, we have average of the second, average of sample came from normally distributed population. This is the true average of population. This is the variance of average values, right? So it's kind of standard error squared. Again, because we don't know sigma, we approximate it using the t-distribution. Okay. Now, what if we want to find out distribution of this value? Well, apparently, you remember we discussed it in block number 3. If you have normally distributed values, if you take a sum or if you take a difference, it will still be normally distributed values. And apparently, in this case, if you take a difference, the expected value will be the difference of the true population average values, right? What will be the variance in this case? Well, we discussed it a little bit, but let me repeat it again. So we need to find a variance of these values of the difference of means. Okay. So this is a slide where we also discussed how to compute variance and standard deviation of sum of z-scores, right? And remember, z-scores are normally distributed. You remember sum of z-scores or difference of z-scores is the same, right? So it's the standard deviation and the variance is the same. And you remember that for variance, the variance of sum of z-scores is n, right? So the variance of one z-score is 1. I mean, if you talk about population of one single z-score is distributed randomly. But if you take several z-scores and compute the variance of this sum of this z-scores, or difference of the z-scores, then the variance will be equal to n. But where this n comes from? Well, n comes from sum of n z-scores, right? So it means that if you have, for example, sum of z1 and z2, it will be the same as variance of z1 plus variance of z2, right? And remember, this is 1, and this is why we get 2, right? So it means that if you have a variance of sum or difference of normally distributed populations, it will be the same as a sum of the individual variances. Okay. Let me show you again. I will not prove it mathematically. I will prove it by using simulations. So in this case, I have average values that came, you can see it's how many? 1 million, I believe, right? It's 1 million values. It's almost the population or large sample. This is the true average, right? It's mu1. And this is, remember, because it's average value. So this is sigma but I call it sigma 1 divided to n, right? And then square root of this one. So this is my standard error for this average values, which is standard deviation of average values, right? So if standard error is 2, then the variance that corresponds to standard error is 4, right? Now, this is my second sample, came from this population. You see average is 180, but the variance is the same, right? Variance is the same. It's 4. Now, I can compute the average of the difference. Average of the difference should be the difference of population average, right? So we expect to see 10 here, and indeed it's 10, right? So it's very close to 10. If I increase the sample size to, 1 billion, it will be almost exactly 10. But what about the variance? Well, according to our expectations, variance should be a sum of these two values, so it should be 8, right? Because variance of this, or standard error squared of this is 4, standard error squared of this is 4, so we assume that the variance of the difference, so standard error squared of the difference of means will be 8. And indeed so. You can see it's 8. Okay. And that leads us to the following. So the difference of two means, or difference of means of two samples that came from two different populations, will be also random value, normally distributed. It will be normally distributed around the expected difference, which means difference of the population average. And then this will be the variance, or standard error if you want, right? So this is variance. And then you remember, it's expected effect. And this is the observed effect. So now we know how observed effect is distributed around the expected effect, right? But that let us do the following. If this is normally distributed, then we can approximate it using t-distribution. You remember, we can approximate any normally distributed values using t-distribution. So in this case, we still have the observed effect, the expected effect. Instead of z-score, we will have a t-score. And instead of this, we have this, right? We have this. So this is our pooled standard error. Pooled standard error. And this is a pooled variance. Okay. So it means that actually we don't need to change anything. We just need to compute the standard error in a slightly different way. But the rest is the same. We still use t-distribution, so it means that we can compute confidence interval and we can make a t-test. But how many degrees of freedom we should use? Well, let's recall, in each sample we have n-1 degrees of freedom, because we lose 1 degree of freedom because of this, right? So we compute S based on the average values that we also compute based on the sample. So it means that here we have, in this case, we have n2 minus 1. In this case, we have n1 minus 1. And altogether, we have n2 minus 1 plus n1 minus 1, or it's equal to n2 plus n1 minus 2 degrees of freedom. So this is how many degrees of freedom we should use. Okay. But again, this is correct only if this is true, because for normality, this will correct for any sigma. But if you want to use t-distribution in this case, so this assumption is important, but we will discuss details a little bit later. Okay. So this is observed effect, this is expected effect, this is standard error of the effect, and then we know the degrees of freedom. So we know everything in order to do the calculations. However, let me simplify it even further, because in our case, you remember, the sample size are equal. And when sample sizes are equal, we also call it a balanced design experiments. Then you can simplify it even further. So instead of n1 and n2, let's use n. And then this is how the standard error will look like. Or you can replace, you remember that if this is square root of the ratio, it will be ratio of square root. So you can do it like this. And let's define the standard deviation, the pooled standard deviation, as like this. So you take a variance of the second sample, variance of the first sample, you take a sum, it's a pooled variance, and then take a square root, right? So a square root of the pooled variance. So in this case, you can see that this expression is very, very similar to the expression that we had for the one sample t-test and for the one sample distribution, except this one. So this one is computed based on the two variances. So now let's do the calculation. So first of all, you remember these are just formulas that we derived just in the previous slide. This is our sample. So let's start with computing statistics. Average value 32.6, standard deviation 2.3. This is what we also computed before, you remember. Average value of the second sample 44.5, standard deviation 3.7. N is equal to 4 because every sample has 4 values, 4 independent randomly obtained values. Now we compute the observed effect first. It's simply a difference of mean values, and that gives you 11.9. Now you compute pullet variance. You remember it's just a sum of individual variances. Because these are standard deviations, we need to square them in order to get the variance. So this is the pullet variance. Now we can compute the standard deviation, right? So this is standard deviation. Pullet standard deviation is simply a square root of 18.98. Right? So this is it. So now we have this one. Degrees of freedom, it's 2 times sample size minus 2. It's 6 degrees of freedom. So it means that we can compute a t-value for 95% confidence and 6 degrees of freedom as 2.45. How I got this t-value? You remember that, again, if you have 0.95%, 0.95 here, so you have 0.025 here, 0.025 here. So for example, this t-score will be computed as qt, 0.025, and then 6 degrees of freedom, but it will be negative, right? So if you take a positive of this, then you will get 2.45. And now we have everything to compute confidence interval. We simply compute error margin by taking a t-score, multiplying to standard, pullet standard deviation, and then divide it to square root of n, right? So this is your error margin for 95% confidence, and now this is the confidence interval. So this is the expected effect. We observe 11.9. We expect it will be somewhere between 11.9 plus minus 5.3 with 95% confidence. So this is our expectation. Now you can also make it as an interval. 11.9 minus 5.3, it will be 6.6. And then 11.9 plus 5.3, that will be the 17.2. So this is the expected effect, theoretical effect. Now let's do this also by using R, by using built-in function. You remember we have a t-test function that we used for one sample t-test. It can also work for 2 sample t-tests, and this is how to use it. So first we define 2 vectors for 120, for 240 seconds. And now we simply provide these 2 vectors to t-test. With one sample t-test, we provided only one sample. Here we provide both. And you can see this is the important to tell that this rule is met, right? So variance equal to true. And then you can see I don't want to get all output. I want to get only confidence interval. This is why I add this $conf. You can simply try this on in your R console. And this is what I got. You can see 6.67 here and 17.2. So it's very, very close, despite that we rounded a lot of values. So our calculations, manual calculations, are not very precise. You can see that we got almost identical values by using the t-test function. Okay. Usually we visualize these kind of things using a special plot like this. You can see that this is a particular effect we observe. So change in time from 120 to 240 seconds. So you can see 240 minus 120, meaning average of 240 minus average of 120. This is the observed. So this is M2 minus M1. And these are the confidence intervals. So these are these boundaries, this one and this one, the left and the upper and the lower boundaries. Okay, so this is actually the percent of popped corns. Okay. So that's how it works. So now we can estimate, based on the observed effect, we can estimate the confidence interval for the theoretical expected effect. And in the next video, we will discuss how to make a test.